Exactly. So if you estimate by radial approach, 5 firms are efficient. And these 5 firms are this one, this one, this one, that one, and then that one. Okay. Out of those 5 firms, 2 of them are weakly efficient because they are on the free disposable section of data. Now listen, if you estimate the efficiency of these 5 firms, they will give you a score of what? If you estimate the efficiency, they'll give you a score of what?
1.
1. Now listen. However, if you estimate the efficiency of this one there, the free disposable section, by the SBM, the slack-based measure, whilst the radial measure will give you a score of 1, the SBM will give you a score of less than 1. Why? Who can guess and tell me why? 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 Steven.
No. Okay.
No, because
Yeah, Steven.
yeah, it's because that firm is operating on the free disposability line and it has slacks.
Exactly. So why does the slack-based measure gives you a score of 1? That's my question. Sorry, why does a slack-based measure give you a score of less than 1? Why? You said because it contains slacks. So what does it do with the slacks?
Doc, it takes into account the slacks and hence does not, in a way, count the slack as part of the efficiency.
It incorporates the slacks in the computation.
Yes.
That is it. It incorporates the slacks, and the slacks are going to be a kind of a reduction in the score. And so the SBM is said to be much more discriminatory than the CCR and then the BCC. The SBM is much more discriminatory, which means that it doesn't just give you many ones. It doesn't just get up and give you many ones. It's much more discriminatory. So take note of that. Because the SDM has got a lot of advantages, and I have a complete lecture note on the SBM. So take note of that. Okay, so today what I want to look at now is I want to go to the R estimation. And this is where we got to the last time. We were able to estimate this. Go and understand and watch the videos and learn how to compute all of the, what do you call it? Learn how to compute all of the R commands and everything. So what I want us to do is to estimate the DEA efficiency scores. We'll start with the constant returns, then the variable returns. Just to familiarize ourselves with it, I'm just going to run the commands again. They are all there though. We did this plot, and then we got to this section here. So what I'm going to do now is to estimate the commands. Okay. I'm going to estimate the efficiency scores. So the first thing to do is to write this command number 17 that you see here. You see the command number 17?
Yes, please.
Okay. Which orientation am I using?
C, input orientation.
Okay. Now, guys, listen. If we are doing this input orientation, without you knowing or with you knowing that if you look on the right-hand side, you will notice that apart from the returns to scale and the orientation, there's something we call X ref and Y ref. Do you guys see that?
Yes, please.
The X ref and the Y ref, these are the indicative of what you are using to form the frontier. That's what it's indicating. What is forming the frontier? And when you do X ref and you want all the inputs to be used, the coordinates of the inputs to be used to form the frontier, then you will now indicate those inputs. And in our own, those inputs are represented by X. So I'm going to do two things for you. I'm going to copy this thing that is here, okay, for the constant returns to scale estimation. I'm going to copy it, the same thing, and this time I will bring in the X ref and the Y ref because I want to see how the results usually show. So after this true, I just want to attach one which is X ref and the Y ref. Now I'm going to run the first command, which is a 17, which is a constant returns to scale. The constant returns to scale says that it is, I could have used any word. Instead of CRS, I could have simply called it anything like K. Okay. So it says that the DEA command for that is use your X matrix and the Y matrix, and then change the returns to scale and the orientation. You want the slacks to be incorporated, to be calculated. Okay. And so let's run that command. Once you run the command like this, you go and highlight that part, just the first part of the equation, the left-hand side. And then you run that as well. When you run that, it will show you the results. Okay. And I'm sure you can all see the results.
Yes, Doc.
And I think this result is different. Yeah, it is different. And the reason why it is different is that it's using a different data set I used to have before. Okay, let me go and check the data set. Two, 5, 1, 2, 2, 2. Do you remember the data set we were using? Yeah, because that one is different. Look, let me just show you. Okay. Check the commands. Okay. If you check the commands, you see that all of the firms are efficient except DMU5. You realize that?
Yes.
I think because I've been working the other our data set. So I need to know the data set that I used. Because it appears that the R is taking a different data set that I used.
Oh, okay. This is the first one is 3.5. The second one is 3.3. So it's different. What we use to draw this frontier is different from what is in R.
So guys, let me just give me a second. Let me get a right data set. That is actually what happens when you are doing thousands of things at the same time.
In R.
R. And it's also nice when you're doing thousands of things at the same time.
But Doc, you could have picked the data afresh, anew.
I'm picking it anew now.
Okay.
I'm picking it anew now. The only thing is that the machine is a bit frozen.
Dog, I think 2022, you have to get a Mac computer. A Mac desktop, I mean. Reason, they don't freeze like that.
So this is a data set. I'm sure when you look down in the console, you will now see the data set.
This is it.
And then we're able to run all of these things. Let me just, and then this is the result. Okay. This is a result of the technical efficiency. And you can see that they are all 1, 1, 1, 1, except the DME. Now, so at this reference, I'm going to use the X, okay, to represent the X reference, and then the Y to represent the Y reference. Okay. In fact, let me use a different name for it. Let me call it like capital U. And I show the results for the capital U. You guys will notice that it's using the same answer. You realize that?
Yes, dog.
But in your real life, like you should. In your real life, what is happening is that you are letting the frontier be defined by the X and the Y. Okay. And this is interesting and important because when it comes to MAMQuest and other definitions, what happens is that what you use to define the frontier is important. So the X and the Y are being used to define the frontier, but we didn't show them in the earlier command. We didn't show them in the earlier command, and I want you to know that implicitly, that is what is defining the frontier. All right, so let's go to the next command for the VRS. Okay. When you look at the VRS, the only thing that changed is the RTS, the return to scale. Okay, and when you run that, you will see that in this very example, the VRS scores are the same as the CRS scores. You notice that. And so we can find the scale efficiency, and scale efficiency is a CRS scores divided by the VRS scores. This next command, which is TECRS, okay, and then TEVRS, that will give you the CRS. If you highlight it and show the results, you see that they are all 1, 1, 1 because the VRS and CRS are the same. The next thing is the command number 21 here. This command simply summarizes the data. So if you want your results to be summarized, I am choosing to summarize the CRS. Okay. You do that and it will show you the results, as you can see down there. It tells you that summary of efficiencies, and it tells you that it is constant returns to technology. It also tells you that it is so input oriented, and it gives you the number of firms with efficiency score of 1. And how many are they? They are 4 out of the 5. Now this one might not look so important, but when you have thousands of DMUs, that's where you know that this summary is good. And then it gives you also the mean efficiency. And then it tells you the ranges, most of the quartile ranges. Okay. And that gives you a summary of the minimum and the maximum values and the medians and the means. Okay. The next thing to do is you can put all your answers in a data frame. And I'm calling it something like EF. So I'm giving it an EF to indicate I want to put everything into a data frame. So once you make EF equal to data.frame, you will rename the constant returns to scale. I decided to call it T. So you bring a C into bracket, the constant returns to scale, you're going to put it into a column, okay, hence the C. And we are going to show the result as T. For the variable returns, we're going to show the results as pure technical efficiency, which is a name in the literature. For the scale efficiency, we are just going to call it SE. And then we'll run the results in 3 decimal places. Okay, so once you do that, okay, and you run the results in 3 decimal places, you get this thing down here below. So you can see that you have your technical efficiency, the pure technical, and the scale. And you can export this, or you can just copy and paste it into R and nicely show the results. Now, how do you do that in R is an important thing. We'll look at that later. Any questions so far? If you have a question, raise your hand or say it. Okay. So learn how to estimate these 3 types of efficiencies. The next thing to do after estimating these types of efficiencies is you can actually show the results by giving some density plots. Okay, you can give some density plot. And what do I mean by that? Well, sometimes efficiency scores, you can use histogram, line graphs and all that. But density plots are good. Kernel density estimations are good. This is something that you have to learn. Okay. So we're going to write a command. We're going to call the command EFF dot, and you can see that it is coming. Density dot dense dot plot. Okay, it gives you that. And we are going to plot the VRS result. The VRS result. Okay. So how do I plot a VRS result? Well, what name did you give to it? We call it TEVRS. So we call it TEVRS. Okay. It shows. You bring a comma, and because it's a plot, you can indicate the line width. LWD line width, let's call it like 4. Okay. And the color, let's call the color red. So you do comma COL equals to the color red. So what this one is going to do is to plot the kernel density of this VRS results. Okay, and the efficiencies are bounded. Note that efficiencies are usually bounded between 0 and 1. But here in the kernel density estimate, the efficiency are bounded either above, okay, above for the input directions, or below for the output direction. And you will later learn, if you dig deeper into the kernel density estimations for efficiency, you will learn that it's based on the reflection method, Silverman reflection method in 1986. Okay. And then there is a default window kernel and a default bandwidth, which is already in there. One paper that has really used the kernel density is our paper, my paper with Charles Texan in 2017, okay, in energy economics. Also, the paper by Totosa Osina et al., 2008, which was published also in eJob. They also use kernel density graphs. It's becoming common, but of late, those of you who are in this research group, you know that we have changed that a little, and we are using a different graph in addition. Okay, so let's run this result to see how it is. Okay. When you run this result, this is what you see on the right there. You will see that the densities on the vertical axis, the efficiency, are bounded between 0 and 1. Okay. And you can see that the density, if you look at the scores, you will see that most of them had a score of 1. Do you realize that? Most of them, DMUs had an efficiency score of 1. So that is why you see that at 1, the density is high. Okay. Sometimes when people are reading these densities, okay, they don't know how to read them. But this is it. At that section of 1, okay, let me just do it. At 1, you will notice the majority of the firms are, the density is very high at 1. That's one first thing you will notice. which means the majority of them are having a score of 1. That's the first thing. The second thing is that the normal distribution curve, the curve, the curve is exhibiting multimodality. Okay. In other words, there appears to be one mode happening at this section here, and it appears that at the one, another mode seems to be appearing. Okay. So it is not fully normally distributed. That is why we always say that efficiency scores are skewed. Okay, the distribution is not normal. Okay, the distribution is not normal. So those are the quick, sharp things that you know. And of course, you have the efficiency scores showing, and you can see that the average, in this case, the average efficiencies, you know, is where the line is quite high, and in this case, it's moving towards 1. Of course, when you look at the mean, it tells you that the average efficiency is around 93%. Okay, so again, it is somewhere around towards that one here, okay, that section here. All right, but when you look at those papers, you'll be able to find more of what we mean when we talk about kernel density estimations. Apart from kernel density estimation, once you've got your results, another thing you can work on are the peers. The peers. Okay, so who are the peers of the DMUs? Who are the peers? So the command to do the peers is simply peers. That's it. The command to do the peers is simply a matter of typing peers. So you type peers into brackets, the name of the efficiency you're dealing with. Okay, let's use the VRS, so TVRS. You type PS TVR, and then you run it. And so you get these beautiful results that you see here. Now, sometimes, depending on the DMU structure you are using, it will have peer column 1 and peer column 2 and peer column 3, depending on the DMU you're using. But here, it's not having that. So what does the peers mean? Well, if you look at the results, it will give you something. You will notice that the first column is the DMU names. Okay, that's the first thing that you see, the first column. Now, it doesn't really mention it, but it is implicit. It doesn't tell you that, but you will know that is there. So when I go to this section and I try to, that column here, that first column, that's the names of the DMU. Okay. Now, you will notice that you will have peers 1. Okay. And like I said earlier, if there are other peers, they will also be showing. What does peer 1 mean? What that means, and again, if you can remember, just close this and show you something. If you can remember, just by looking at the graph, okay, it means that every firm had a peer of, in other words, one particular firm. Every firm had one particular firm as its peers. So if you look at DMU1, which is the one on the left-hand side, I just want to use some things to denote them so that you can enjoyably receive them. If you look at DMU1 here, okay, it is using DMU2 as its peer. It is not having any other peer. That would have been peer 2. It's not having any other peer again. If you look at DMU2, it is using itself as its peer. That's what you see there. Okay, itself. If you look at DMU3, it is using itself, and you can see it on the graph. Okay, the peers are the role models. So DMU3 is copying itself. If you look at DMU4, it is, if you look at 4, actually 4 is on the frontier. It's efficient in the final sense, but it is weakly efficient because it has some slacks, a slacks of about 3. And so because of that, it cannot use itself as a peer. It is rather using DMU3 as its peer. And then if you look at DMU5, DMU5 is totally inefficient. And so it is also using DMU. DMU3 as its peer. So you can see that DMU3 has been mostly used as a peer. But of course, there are two peers. DMU2 is a role model. DMU3 is a role model. And interestingly, each firm had one peer. But sometimes you got a situation where DMU1 is using maybe DMU2 and DMU3 as its peers at the same time. So understand the principle of peers is very, very important. Peers are real DMUs that are efficient. You can see them with your physical eye. You can, if they are companies, you can see the buildings. So they are there, they are peers, they are role models, they are reference sets that are going to help you to be able to reach where you want to help. Now, the benchmarks are really the values you should have, but the peers are the real DMs. So the benchmarks are like the hypothetical targets. Okay, the targets you should have, but the peers are the real firms you should emulate from. Okay, the real firms you should emulate from. All right, so that is one thing the software is able to do for you. The next thing is you can tell R to tell you all the number of peers. Okay, get the total number, the number of times each firm, each of the fully efficient firms was used as a peer. Okay, how do you do that? Well, it's a very simple thing. You just type get dot, and when you start typing, okay, sometimes it comes. You type get dot number. Oh, there you go. Get the number peers. Okay. So what you are asking R to do is that tell me the number of firms that were used as peers. And we have to specify which efficiency you are doing. So let's see the VRS. And when you look down there, you will see it is giving you the answer. So we know that DMU2 was used as a peer. Okay. And that's what you see down there. How many times? Twice. We also know that DMU3 was used as a peer. How many times? 3. Please note that you can have DMU, one particular DM being used multiple times as a peer. Now that tells you that that guy is a true role model. And sometimes it helps you to know how to rank the firms. Please put this down somewhere in your note. You can therefore use the peers as a way to rank managerially, give it managerial advice, okay, to know which firms are the best or doing the best. Because a firm can be efficient as one, and another firm will be efficient as one in the Vrs sense. However, if you don't go and check the peers, you will not know that, oh, one of them is really cannot be a peer because it's on the free disposability section. So peers help you to know, to do proper ranking. Note that point, proper ranking. And one of you who is doing that, the SBM and all of that, you'll be incorporating that peers into your analysis. So please take note of that. Okay, I'm sure you get to the principle of peers. Now, let me ask you some few things. Okay, now we are going to generate the last one, which is called the slacks. You remember we indicated in this firm which ones are the slacks. If you actually check the graph, you will note that DMU1 is on the free disposability section, and therefore it's exhibiting what? Slacks. I just want to show you DMU1. Okay, that's a DMU1. It is experiencing slacks. And then DMU4. DMU4 is also experiencing slack. DMU5 is inefficient, but when you trace it, it will hit DMU2, DMU3 automatically, and therefore it is not exhibiting even a slack there. So the question now is, how do you command the R to give you the slacks? How do you do that? How do we tell R that R, I want you to give me the slack? Well, let's give the name of the slacks to be SL. Okay, SL. So you type SL, then you do equal to slacks. And of course, when you start typing, it will come. And what you are now going to tell R to do is I want the slacks for the entire data set of X Y, and then the efficiency. The efficiency scores that you are having there, which is T, let's say VRS, TE-VRS. Okay, and so R will give you the slats. Watch it. Okay. I've run it to see the result, just highlight the Excel, and you will see that the first one is the DMU1. And you can see that he's telling you that the DMU1 has a slack of what? 2. The DMU2 has a slack of 0. DMU3 has a slack of 0. DMU4 has a slack of 3. And then 5 has a slack of 0. Now, you would normally want the fact that a particular DMU has no slack. You would want them to have 0 slacks. 0 slacks is always the best. So the ones that have 0 slacks are good. Usually, they are the ones that are inefficient. They are the ones that are near. But not all of the slacks, this is important, not all the DMUs that have 0 slacks, not all the DMUs that have 0 slacks are PS. So you can see that DMU5 has a 0 slack, okay, but it is not even efficient. So it is not the fact that, you know, if you have a 0 slack, it means that you are efficient. Okay, but for you to be having a 0 slack, your efficiency score must also be equal to 1. So to be a peer or a role model, first of all, your efficiency score must be 1, and you must have a 0 slack. That is when you become a true peer. Now that I've created a slacks, you can put all of the data set together. Okay, so let's create a data frame. Let's call it data.frame. We are putting everything together. Data.frame. Data.frame. And then you put into brackets the same names we gave earlier on. Okay, I'm putting everything together with a C. I'm just dropping it there. But now I've added some few things. So I want to add those few things. The first one I have added are the slacks. So I'll just write SL, which is the name we give to the slack, $, then slack. You see the slack has come. And select, okay, SL $slack. That is for the whole slack, okay, whether it's input or output, but I want only input as well. So let's do SL $, the input slack, okay, which is okay, SX. And then you do the same thing, SL $, for the output slack. So if there is an output slack, indicate that. So we want to have all of this in a data frame, and I'm going to show the results right now. Oh, beautiful, there you go. So you can see that efficiency scores are the first one, the pure technical, the scale, then the slacks. The slacks here is telling you whether that firm had slacks. So you can see that when it says true, what it means is that that particular DMU experienced slack. And you can see that DMU1 had a slack on the picture. You can see there. So that's why it's true. And DMU4 also had a slack. You can see it on the redisposability section of the graph. And so the question now becomes, where are those slacks? Well, the first one is, are the slacks on the inputs or on the output or on the other input? Okay. Now you can see that the output, none of them have got an output slack. And there's a good reason why. But for the input, you can see that the DMU4, its slack is on the X1. So it means that he's using too many of X1. So he has to carry it down by 3. But on the DMU1, if you look at DMU1, its slack is on the X2. And so it means that he has to reduce the X2. So this data frame can now be sent to Excel. And then you can now have a beautiful managerial or academic exercise to indicates right there. All right, so I'm going to ask you a question. Let me take you back to the slides, and then I just ask you some few questions. So the question I want to ask you, and I want to give me an answer if you have been following me, okay? DMU5 has an efficiency score of 67%. Who can interpret that score, what it means? What does a 67% efficiency score mean for DMU5? What does it mean? Theophilus, remember we have interpreted scores before.
Yes, sir.
Okay, try and let's see.
So that means, Doc, DMU5 must reduce the input level by, that is 1 minus the 0.65. So that is by 33%. And then hold at the output level being constant so that it will be efficient.
Oh, good, you have an idea. So what it means is that the DMU5, generally speaking, should be able to reduce each of the current input. In this case, yeah, X1 and X2. Okay. Each of the current input proportionately. Okay. Proportionately, because we are dealing with a radial measure. It has to reduce those inputs proportionately by 33%. By 33%, without reducing the output level, okay, by keeping the output level constant, in order to become as efficient as its respective efficiency references, in order to become as efficient as its respective peers, okay, and therefore to achieve the targeted level. When you are doing a normal industry, you use the mean and then to define the interpretation. So learn how to do that interpretation. Exactly what he said. They are down here. Okay. There's one more thing to do apart from the interpretation, and that is lambdas. Lambdas and targets. And that's the last thing that we will do. What are lambdas? Well, lambdas are the weight of the peers. The relative importance of the peers. Okay. So a peer will have lambda. If you are not a peer, you won't. So let's go and then get some peers to see whether they have lambdas. So if you want the lambda, just type lambda. Okay. And then you take the efficiency score that you are dealing with. So let's see which ones. So if you look at DMU1, okay, it is having L2. L2 means that FEM2, it is using FEM2, it is putting weight on FEM2. That's what it means. And how much weight, how much lambda is it putting on FEM2? Remember, this is an envelopment model. It is putting 100% weight on FEM2. So what it's saying is that all the importance I need to look good, the only thing that is important to me when I want to look good is DMU2. That's what DMU1 is saying. So it's putting all the point. DMU2 is also putting all the weight on the same FEM2. That is why you have L2. L2 means that the lambda for FEM2. And then DMU3, 4, 5, they are all putting the weight on DMU3, the lambda on 3. And so they are also putting 100% weight. I must say that sometimes the weights are not 100%. So sometimes a DMU2 will put maybe 67% weight on lambda 2, DMU2. And then will put the rest of the weight on DMU3. So sometimes they will split them. But for this very example, we see that they are all putting 100% weight. But note that the total number of weight, when combined or across each particular firm. So when you look at DMU1, if you check the weight, when you combine all the weights together, it should be equal to 1. It should be equal to 1. So that is lambda. It's very important to know lambda because now it helps you to know Lambda helps you to know which firms are the peers, because at the top, you see L2 and L3. That is what is telling you that they are the peers. Okay. Now that we have gotten the lambda, let's add the lambda to our data frame. Okay. So I'm going to copy this data frame again, and then you will have this. And at the last section, I'll just do a comma. And then after doing a comma, I will type lambda. And then I'll put the names, okay, lambda. And then you put into brackets TVRS. So I just want the VRS results. So I want the lambda of the VRS results. Okay, it looks like I did this twice. I just want to delete one. Okay, and then you run it. And there you see, at the bottom, you see that you put everything together. You're able to take each particular file. I can even add a data set. So in front, I can just add the name of the data set, which was what? Farm. So I can just add farm and run that. So now it gives me the names of the data, X1, X2, Y1, their prices, the scores, everything nicely packaged together with the lambdas. So this can now be beautifully exported if you want to, and use it for further modifications. All that. Okay. There's something little about the lambda that you should note. And it is something that is for basic academic exercise. Okay. Basic. And here it is. If you look at the lambda for DMU1, okay, it means that DMU, for DMU5, if you look at the lambda, we checked it earlier, it was 5. It was 1. What does that mean? It means that DMU5 is putting all the 100% weight on that lambda 3 or DMU3, which means that you can use DMU3's lambdas. Okay. DMU3, you can use its 100% lambdas to find the target for DMU5. So DMU5 is inefficient, and it wants to copy from somebody. It's now copying, in this case, from DMU3. So the lambdas for DMU3, so if DMU3 has got some lambdas, these lambdas are going to be used together with the input of the inefficient DMU, in this case 5, to get to the target. So as an example, the target, the virtual is simply the weight multiplying by the input or the output. The weight for DMU, any of the DMU, the virtuals for any DMU is the weight times the variable. Now, if you want to know the target of a particular input, say X1, okay, it is going to be the summation of something times something. That is the lambda of the peer, okay, the lambda of the peer multiplied by the input of the peer. So if I want to find a particular target for DMUA, I have to note who are those that DMUA use as his peers. That's the first thing. Then those peers, they will have their own lambdas. So what weight did they give to them? What weight did they assign to them? And then you will now identify that weight. That weight is a lambda. You will now come and multiply that weight, okay, by the input of that DMU. Okay, so in this case, the DMUA, to get the target that DMUA will have to arrive at. Okay, so the key point is that only the role models can be used. The role models will have a positive lambda, as I said this earlier. Okay, and they will now serve as role models for inefficient ones. So you can use the lambdas plus the variables to arrive at the target. That's the key point. All right, so that ends the lecture on the nitty-gritties of the results in R. And I'm sure you hopefully I've been able to give you some tidbits that will help you to know the basics. We'll get into the nitty-gritties, the complexities, and even the further development of the results of the models. That will help in this regard. Okay, further development. All right, remember, drink deep or taste not the Pierian spring. Their shallow drought will intoxicate your brain, and drinking largely severs your headache. You either drink deep or you taste not the Pierian spring.